Okay, so welcome everybody. It's a pleasure to have for the astrophysics talk today Laura Sommovigo. Laura got her PhD in Pisa, where I met her, in 2023. And then she moved to New York to CCA Flatiron, like in 2023 in the fall. And now I think she will move in a few months to Columbia to finish the fellowship, because it's a joint fellowship between CCA and Columbia University. And today she will talk about a favorite topic, I guess. So that's in the reionization era. I will tell you in 5 minutes.
Okay, thank you. Okay, so hi everybody. Sorry. Okay. So hi, I'm Laura. Let's see if it works. No, it doesn't work. Okay, so first of all, I'd like to tell why you should care about dust. I know that there's a lot of people in the room, some experts and people who care about dust, but not everyone does. So the reason really, in my opinion, is summarized in this sentence, and it is that the true observables of galaxies are spectral and photometry. It's not stellar masses, it's not star formation rates or metallicities. These are quantities that we get from SED fitting, but the true observables are the spectral and photometry. And dust crucially shapes the emission of galaxies. So for instance, to reproduce the observations of this local galaxy, M82, of whom you see a beautiful multi-wavelength image in the background, data here in the plot are the white points. If we were to only account for stellar emission, we would be completely missing the data in the short wavelength side, because we have an excess of emission in the short UV and far UV wavelengths, and we are completely missing the emission in the restraining infrared. The reason is exactly because we are neglecting the effect of dust, and the effect of dust is twofold. There is somewhat of a passive effect, which is that of scattering and attenuation, which ultimately reduces the amount of stellar emission that leaks out of a galaxy, and also changes the so-called UV slope of the spectra, which is this beta that you see here, which is the index of the power law with which you generally fit the spectra in the UV wavelengths. And it changes it from so-called blue UV slopes to so-called red positive UV slopes. Okay, so these grains, they attenuate the dust, they absorb some of this radiation, so they get heated. And as a result, they also re-emit a portion of this radiation as thermal emission. So you can think of this as a sum of gray body emissions. And now you can see that we can also explain the data that we have in the restraining infrared and far infrared. And now combining the effect of dust in attenuation and the effect of dust in emission, now we can very well reproduce the observations. So now this was a local galaxy. Of course, when we move into the high redshift space, or what used to be the high redshift space, so epochal reionization, things get a bit more complicated. So the first time that we really had a chance to observe these galaxies was with the Hubble Space Telescope. And what we were observing was essentially the stellar emission from these sources. And what we saw is that they were very blue and have very blue UV slopes. So the general idea and interpretation was that these galaxies are being young and formed so early on, they're big metal poor and last free. But in the 2010, enters ALMA and new generation sublimeter interferometers, such as also NOEMA, and we have the so-called dust budget crisis, which is a general term that we use to refer to the fact that we started to see a lot of dust and infrared emission even very early on in the universe. I picked here some examples of some findings that to me are a bit extreme and surprising. For instance, we have large dust reservoirs as early as redshift 8, so well within the first giga-year of life of the universe. These are results by Tamura and collaborators. We find fully dust-obscured galaxies that were missed in the UV as early as redshift 7, and I'm thinking here of spectroscopically confirmed galaxies. And then we have results that suggest that the obscured cosmic star formation rate density, so the contribution to the cosmic star formation rate density due to obscured SFR, could be as high as 30%. So the picture becomes a bit more blurry, and now enters James Webb, providing some contrasting evidence. So on one hand, we have, again, very blue UV slopes, even bluer to some extent than HST was finding at early redshift. But at the same time, we have, oh, nice. We have some heavily attenuated candidates, although they are not confirmed yet by Giulio Redigliaro and collaborators, as early as Redshift 10. And then in terms of, I cannot not say that when we are talking about red galaxies and obscuration, there's the little red dots, although now we are starting to maybe think that this is not due to dust, but could be an effect of dust. I'm not going to talk about little red dots today, though. We also have some tentative evidences of evolution of dust properties in the early universe. You might have heard about the whole discussion about the UV bump, the 2175 angstrom bump being there or not for high redshift galaxies, and in general, the attenuation curves slopes evolution with redshift. And finally, we are starting to get constraints on metallicities of these galaxies, and we find metallicities up are even at redshift 7. So overall, there's a bit of a, I would say, fuzzy picture where we don't really understand if how early on galaxies get enriched and if we really at this point have a crisis still or not. So this is what I'm going to try to do today and try to really just focus on the answer if how much dust is important for interpreting high redshift galaxies properties, how well can we infer the dust of galaxies from observations, who drives the build-up of dust in these sources, and finally, if we still have, looking at simulations and theory, if we have crisis, or maybe we are relatively able to explain observations. Okay, so when I started my PhD, these were the only detections of dust that we had in the first giga year of life of the universe, so I didn't have much to work with, but then comes REBELS, and really increases the amount of detections that we have of dust in the high redshift universe. But REBELS itself was the successor of another successful program and would not have been possible without it, which is ALPINE, which also looked at massive sources at around redshift 5. And if we look at the targets here, I know here there's many ALPINE people, so probably I don't need to say this, but this is the UV magnitude versus redshift of ALPINE and REBELS targets. And essentially what you can see is that both with ALPINE and even more so with REBELS, as we are at slightly higher redshift, we are really looking at the UV brightest sources that we could find in the high redshift universe. So the more massive, the brightest. And the idea is really just feasibility. You want to see many of them. So that's what we can work with. And we wanted to also get spectroscopic confirmation. So we went for C2, which is a very bright far infrared line that many people here like, and also the underlying continuum to try to get some constraint on the dust content. So for me, that I'm a dust aficionado, the big result here is that we got the first statistical sample of dusty galaxies in the early universe, thanks to the combination of these two programs. But unfortunately, there's also a major drawback that since we only got dust underlying C2, we only have a single continuum information. Now, maybe this doesn't seem a major problem, but anyone who works with dust knows that already if we make some approximation, this is the formula that we can use to describe the infrared emission, and say that we know the redshift of our source, so luminous distance. We really believe our dust model, so we say we don't have uncertainty in the opacity, which is already pretty optimistic. We're still left with two unknowns, being the dust temperature and the dust mass. So if we have only one observation, we very clearly understand that we have a problem. So in this 2021 paper, which includes several people here in the audience, what we suggested was to use the C2 luminosity as a proxy for the dust content, essentially writing it as a dust to gas ratio, which we consider to scale linearly with the metallicities of galaxies based on many local observations, and C2 to total gas conversion factor, essentially inspired by Anita's work. Okay, we derive an analytical formula for this conversion factor. We don't just use a constant value, but if you're interested, we can enter more into the details. But the point is that since we use the C2 to constrain the dust mass, then we can use the underlying continuum to constrain the dust temperature. This is an example just to show you that this method seems to work. This is the dust temperature obtained with our method. So only using one continuum information. And this is the dust temperature that you would get with traditional SED fitting, having multiple infrared information, multiple infrared continuum data points. And you can see that in all cases, we are within a 30% uncertainty. You might wonder why these gray points here have such large error bars. These are the high redshift galaxies. The pink points are instead local galaxies for which we had C2 information. Okay, so we can now constrain, using this method, we can constrain the dust masses of this large data sample between ALPINE and REBELS, so we can try to address who is producing the dust in the early universe. The usual culprits for any dust production are massive stars, so AGB stars or supernovae, and then we have dust growth. Now, for very high redshift galaxies, when the stellar ages are generally below 100 mega-year, AGB stars really are going to be subdominant. So what we generally look at is supernovae and dust growth. So here you see predictions from different analytical models, similar analytical models for both so galaxy evolution that also include dust. And what I want to stress is that these dashed lines here are maximal dust production constraints. And when I say maximal, the reason is that they have stellar production, they have growth at the shorter time scale in the range that they decide to explore. They have no destruction in the reverse shock, in the supernova reverse shock, and they have no ejection ever of dust in the galaxy. So it's really a very optimistic, very maximal kind of constraint. The solid lines instead are fiducial results with more typical assumptions for growth, destruction, and ejection. Okay, so when we add our data points here, things are a bit complicated. So you can see that there's a few points here that are above these maximal dust production constraints that I mentioned. So these very already extreme constraints for how dusty a galaxy can be. But you can also notice that we have very large error bars. And indeed, if we go back into looking into these galaxies and change the star formation history that we use, and specifically use a non-parametric star formation history, I have backup slides on this if you're interested. But what we find is that these lower mass sources actually have a preferred solution with an older stellar population and then a recent burst, which ultimately results in their stellar mass being higher. And so now they get pushed rightwards in this plot, meaning that they are now consistent with at least the maximal dust production constraints. Still, there's another point, which is that if you look at these models, we always expect that galaxies that are more massive, produce more stars, are also going to produce more dust. But if we look at the data points, they are really flat. But now this could be that we are really probing a limited, so essentially observational bias, we are probing a limited parameter space. So what we can do is to also add the data points from ALPINE, analyzed with the same method. So we're doing a consistent comparison here. And now you can see that by probing a bit higher stellar masses, we now recover this linearity with more massive systems having also more dust. You can see that also here we are generally below the maximal constraints at least, so we are not really breaking anything. But there's another source of uncertainty that many people here struggle with, which is that of dust temperature. So for us here, we have used this C2-based method that we introduced to get the dust temperature, but another work by Francesca here had used the Milky Way temperature, because that's, I mean, you necessarily need to make an assumption. You have, as I said, two uncertainties, one data point, so that's what you have to do. And in that case, you would guess much higher dust masses for these sources, because our guess for the dust temperature with the C2 method is actually a bit higher. And in that case, now again, we would run into this dust budget crisis problem where the dust masses would be too large. So personally, I argue that maybe the dust is a bit warmer, so we don't have such a major crisis. But we will have, at least for REBELS galaxies, we now have band 8 observations that have been carried out. So we will be able to test at least if these results from the C2-based method hold up or not. We have a few sources where we already have multiple ALMA bands information, such as REBELS 25, which is the brightest galaxy in infrared from the REBELS sample. And in that case, what we find is consistent. So if you need to remember a number, the dust to stellar mass ratios that we infer here for these massive, surprisingly dusty galaxies is between 10 to the minus 2 and 10 to the minus 3, which for a salpeter IMF, but you can really think of whichever IMF you prefer, implies a 0.121 solar mass of dust being produced in each supernovae explosion. So what we can ask then is this number reasonable or not? And what we want to look into is essentially supernova remnants observations. And this is another area where JWST has actually allowed us to add more data points and really look at the hot components, hot dust component in the supernova remnants. So finding these two higher yields here that are a bit more consistent with what we need to require. Okay, so if you look at this dust mass in the remnants as a function of time, you can see that the range that I was mentioning, so the 0.1 to 1, is really at the high end of what we see in observation. So we are really requiring a lot of our supernovae. And on top of that, anyone who does theory for dust knows that the reverse shock actually acts on much longer time scales. So I personally don't think I'm going to live mega years long. So even if I was going to observe the same supernova remnant at the end of my life, still I wouldn't be able to really probe the onset of this dust destruction. So what I want to say with this is that we are already with these observations, we are kind of pushing the high limit of what we can require from our supernovae. And on top of that, maybe we haven't seen destruction kicking yet. Now, different models have very different predictions for how important this destruction can be. But still, it's just to keep in mind that we really are requiring a lot from our supernovae. So probably we need to account for some contribution from growth. But whenever you have both production and growth, there's a bit of degeneracy. And so different models are going to have different predictions on how important growth can be versus how important production can be. So how can we try to disentangle it? What I think is interesting and promising maybe is that if you look at this compilation of different predictions in the literature for the timescales of growth, this is a compilation from, you cannot see it because there's this text box, but this is from a recent review by Raffaella Schneider and Roberto Maiolino. And there's different recipes, but, oops, sorry. There's a common element, which is a dependence on metallicity. The more metallic your galaxy is, the faster the growth is. So since now with James Webb, we can start constraining metallicities, maybe we're going to be able to disentangle a bit the effect of growth and production. And here I wanted to introduce the new child of REBELS IFU. This is a large program with James Webb where we looked at the most interesting candidates from REBELS with NearSpec. And what is interesting is that now we can get strong line ratios, so we can start to get the metallicities of these galaxies. This is kind of the family picture of the REBELS IFU targets, and these are the actual spectra. This is from a paper from Lucy Roland that has come out just a few months ago in the archive. Okay, so we can try to now look at the dust to gas ratios, dust to stellar mass ratios, accounting for the metallicity information, and this is what is shown here in this paper by Indo Alguera. Here, I know this plot is very busy, so I'm going to try to highlight a few things. So here we have dust to gas ratio versus metallicity, dust to matter ratio versus metallicity, and dust to stellar ratio versus metallicity. The colored lines are the same models that I was mentioning before in the dust to stellar plot that I showed before, dust to stellar mass ratio plot that I showed before. Red points are our rebel sources. The black points are local observations, low redshift observation, and the gray points are local observations. And then blue is other high redshift galaxies observed with ALMA and James Webb. So the idea here is that we were hoping that, again, adding this metallicity information, we could constrain a bit more the difference between growth and not. And something that you can look into specifically is these green lines. So this line is the fiducial model, which includes growth, and this dashed line is the model with no growth. And maybe you can see a tentative consistency more in the scenario with growth. But this is really more at the low mass end. It's where the two models are more different from each other. At the high mass end, where we have our REBELS data points, they're essentially indistinguishable. So what I would say is that we are still far from breaking this degeneracy. So how can we try to do better? One option is to try to improve our constraints on the gas content. So we are kind of using C2 for everything, which I know is a problem, but for dust, hopefully we're going to start to gather more continuum information, and maybe then we can try to move away from this C2 method and constrain the gas masses. For the gas mass, maybe what we can try to use is to use simulations to inform us on updated constraints from, so to get the gas content from C2. This is a recent work by Livia here, so I'm not going to say too much about it, but what I wanted to show here is that she has analyzed these SERRA simulations from Andrea Pagattini at SNS, that also NASA works on, and she looked at the C2 to total gas conversion factor, so how much gas mass you would guess based on C2 as a function of metallicity, and she finds a tight correlation. So maybe assuming a constant value, which is what was done in the paper that I was showing before by Elguera, maybe could be responsible for some of the flatness that we were seeing. So maybe if we don't use these new updated constraints, we can try to reduce a bit the error bars in the points. But there's another issue now on the dust mass end. So I said, okay, with gas mass, maybe we can try to do better with C2. Maybe we can try to get other gas tracers. That's not really my expertise. But we also need to try to do better with dust masses. We know anyone who does theory or simulations, or really anyone who knows that dust temperature is not a single value in a galaxy, it's a distribution. But when we have few data points, we generally fit it with a single gray body. So what we did in this paper that is now today out on the archive with my friend Hiddo was to make a simple model with that fits the PDF of the dust temperatures from different hydro simulations. This is just an example with one of the SERRA galaxies. But then we find that essentially if we use a skewed normal distribution for the PDF of the dust temperature, we can reproduce the mass-weighted PDF and the luminosity-weighted PDF of the simulation by changing the three parameters in our model, which is the mean temperature of our distribution, the variation of our distribution, and the skewness. Okay, now we leave aside the simulations, and what we can do with a semi-analytical model is that we can go as crazy as we want in our parameter space search and really change these parameters as much as we want and have crazy looking PDFs and crazy looking SEDs without actually having to run the simulation to back it up, which is much more expensive. And also when you run a simulation, you don't know a priori what you're going to get. So this is an example. Here we are changing from top to bottom, the mean temperature, the variation, and in the end, the skewness. So the skewness, you can see that it's really a minor effect on the SED, more of an effect on the PDF. So in the rest of the paper, we keep it fixed. So then what we do, focusing on the first two parameters, because they are the ones that affect the SED more, we look at how wrong we can be in the guess of the dust content of the galaxy, so the total dust mass and the total infrared luminosity, when we actually fit the data through an observer pipeline using a single gray body. And this is what you see here for a basic, so-called basic ALMA. We call it basic ALMA configuration, so band 6, 7, and 8 with high signal to noise ratio. And you can see that in this case, we are never really super wrong because of the single temperature approximation, but this is also because the error bars are so large with the uncertainties from the SED fit. If we use our super ALMA configuration, which is band 3 to 10 with high signal to noise ratio, now the errors shrink, and now we start to see systematics. And what I found interesting is that if you have a wide enough temperature distribution, you don't really need to have very hot dust to be wrong to start to underestimate your dust mass, because ALMA bands only probe longer wavelength side of the infrared SED. If your PDF distribution is sufficiently wide, you actually are already wrong, even for cold mass-weighted dust temperatures. So this is to say, first of all, let's be a bit careful whenever we compare data and models, when we call that there's a major tension, because there's this uncertainty, for instance, is not included anywhere, and this can be as high as a 0.75 dex. And on top of that, another thing that we look at in the paper is trying to do this with the different dust models that people have used in the literature. And what we find is that this can increase up to 1 dex the uncertainty on our dust mass guess. So again, what I want to say here is not to say that this needs to just be slapped on top of the uncertainty that we had before, and that this adds to the budget crisis. What I'm trying to say is that when there's a tension between a model and an observation, and is within a 1 dex, I think for now, we cannot really say that there is a major tension. The last point that I wanted to make before I close is that again, as I said, in my opinion, there's no major crisis like this. In the last few years, we have had in literature several simulations that have started to introduce dynamical dust models in, which means that you have dust processes that are associated to different ISM phases. This is an example by Claudia Di Cesare, but there's 2 more from this year by Khaled Choban and Desika Narayanan. The gray points that you see here, these color points here, these circles here, they are all predictions of dust content of galaxies from the simulation. So we can produce dust in the early universe. It's not impossible to do it. And I think there's no, again, major tension in my opinion between data and theory. But we still have a mismatch. So as you could see here, sorry, maybe I changed too fast. Whenever we are comparing observations and simulations, we are really always trying to do a game of picking the few lookalikes. Because for simulations, we really need to try to pick the few at the HIMAS end of simulations. And for the observations, we try to pick the few that are in the same parameter space. You can see it here, here, and here. And the reason is not that simulators are not doing a good job. It's just that if you, in any cosmological simulation, you're always limited in volume and resolution. If you want to, these are all the simulations that are out there, cosmological simulations that we have. And if we want to look at the massive systems at Redshift 7, this is a Stellamos function. If we look at the number counts that we want, these systems are rare. We are looking at massive systems in the high redshift universe. So here we have a 10 to the minus 3. But we also want high resolution whenever we're doing dust and we're doing ISM, right? So we at least want to arrive at the border of resolving GMCs. So we want to be at the at this end of this plot with volumes and resolution of simulations. And you can see that, for instance, if we pick the highest simulation that we have here, which is, I think, SPICE from the MPA group, if you plug this number count here with their volume, you can see that we essentially have one massive galaxy at Redshift 7 in their volume. So this is to say, I don't think we have a major tension, but I do think that we need to try to move more into an apples comparison, try to find ways to get more massive systems into detailed simulations, and or on the observational side, try to push to fainter sources. And this is something that I was happy to see last week at the conference that is starting to be done by Dennis Bulgarella with, for instance, the Galidas sources. I'm going to leave my summary, and thank you for the attention.
So we have time for questions. Okay, can I just say?
One question related to the dust mass estimates and how future facilities, let's say, as PRIMA, that will be able, let's say, also to sample the infrared frame will help to constrain the dust masses. I mean, the second component, warmer one, will be useful.
Yeah, so we are working on a follow-up work of this paper that has just come out. And on my side, I'm going to do a more theory one where I try to associate the free parameters to galaxy properties. But Hito, on the other hand, is doing a work where he's going to try to use this as fit on mock ALMA and PRIMA observations to try to see if in that case we can try to directly from observation, instead of fitting the single temperature, try to use this method and obtain the PDF of the temperature distribution from observation. So it's something we are thinking about. I would say that for super high redshift, I'm not sure we have the sensitivity with PRIMA to really detect individual galaxies.
That with some.
Yeah, I mean, we have experts in the room.
Yeah.
I don't know. I think for Redshift 7, maybe it's not.
7 is
Yeah,
depends
maybe
on,
up to 4.
Depends on how bright is the galaxy, but yeah. Although the imager is quite sensitive, but yeah, we estimate there are mock catalogs with spreads that are cut to the sensitivity of the surveys that we are planning in the PI time, and I think we can reach out to Redshift 7, 8, but probably for the brightest and dustier galaxies.
Yeah, I mean, these are, I always say that these are dusty galaxies, but let's keep in mind that they are UV selected.
Yes.
So these are not like sub-millimeter galaxies or the dustiest out there. They were just surprisingly dusty, I would say.
Is there a critical spatial resolution for simulation to catch up with observation, you think, or just the more resolved, the better?
So what I would say, what I was trying to say with the plot before is that I think at least we need, we at least need this kind of resolution. So I would say below 10 to the 6 solar masses, because that's at the edge of resolving GMCs. So you're not resolving molecular clouds, but going up there. And I think that's at least needed to try to see, for instance, the effect of denser clump versus the diffuse ISM, how this can change your perceived UV slope depending on line of sight for the same galaxy. Ideally, like if I could choose, I would want to go down to single stars, also because if you can resolve, if you can resolve the supernova shock and everything, that would be even better. Because if you don't resolve GMCs, that's also another important part. Like the production is still going to be sub-free, right? You're not actually resolving your supernova. But this, I think, is a reasonable ask to try to maybe use a flares-like approach to try to really zoom in on the overdensities and populate a bit more the MSN at this resolution. I think this is reasonable. Okay, go.
I agree that it is not easy to distinguish between supernova and growth. So in the last few years, there has been growing evidence of deeply embedded star clusters that are very young, ages of the order of a few mega years, deeply embedded clusters. So before supernovas. So people don't talk much about it. It's an exploratory field. But this evidence leads through probably goes against an important role of supernova and in favor of growth. But people, some others are considering the role of pre-supernova sources, just like Stella, like Wolf-Rayet, that traditionally they were considered negligible in terms of dust production. But some new papers that came out in the last few years seem to stress their possible role as important pre-supernova process.
Do you know what kind of observations are trying to constrain this battery straight up?
They are
These are
total number, some ALMA observations of infected of very young stellar aggregates that are very luminous in the infrared, something like that.
Yeah, I mean, as I was saying, we are kind of asking a lot of the current dust production models that we have. I don't think there's a major tension, but we are definitely pushing it. So anything that we can add to have a bit more room.
No, Roberto, just because I saw him before.
That's very nice now. I was going to challenge a bit one of the last statements to say that concerning going for the smaller, more representative galaxies, and I was wondering from an extremely biased perspective if if there's more to learn from the extreme sources, working a lot with high-energy quasars. We have now a lot of them where we have a decent sampling of the dust density, so we understand a little bit the temperature and so on. And these are very extreme sources. It's not uncommon that we have several times 10 to the 8 solar masses. That's few hundred megayears from Big Bang. I was wondering if pushing the limits of the model would be an interesting test in that respect, because they're very massive and we have to do everything very heavy, or they're so rare and so peculiar sources that seem
I think
glory.
I think it depends a bit on what is the method you want to use to do it. I think if you want to go for finding it in a Cosmos sim, because of the point that I was making here, that you need this kind of resolution to dust processes properly. Yeah, it's really hard to find this kind of very rough subsistence in a statistical number. But if instead you want to use semi-analytical models, that's already a bit easier. Then you can try to stress test the models that you have and changing parameters and see what produces best this kind of observation. So I would say it depends a bit on the first analytical model, which is an interesting place to look into. For a simulation, maybe not so much when we're going for this. Yeah, but even with this means, like for instance, the Chodan one that I was showing before, these are zooms from fire, but even there they are still at the low mass end with respect to observation. So I'm sure there's people that are working on that specifically, but from what I've seen so far, we don't have happy for it.
I think we have time for a very quick question.
Yeah, it's just like, if you want to ask, actually, it's like, but at which metallicity has the better stuff?
I think they are local observations.
Because the point is that, if there are a large metallicity, then supernovae are old, our could be like net dust destroyers, but at lower metallicities, like they are net dust producers, so it's a bit, those are just very good.
Yeah, and the low metallicity, the suggestion to go towards low metallicity is also in terms for disentangling the growth. Because as we said, the growth is always inversely proportional to metallicity, so low metallicity growth is very slower. So either if you go to super high redshift 10, where you're expecting metallicity to be lower, or just to peak low metallicity systems, maybe that's where you can really try to test production with no observation.
Yeah, but also the observations of embedded star clusters or systems in low metallicity galaxies. Low metallicity galaxies are it's like again exploratory.
Yeah.
Very hard.
Yeah.
There are very few observations of very low metallicity dusty galaxies, and this is one of the cases brought up by Prima, essentially the study of the exploration of dust in very low metallicity systems.
Yeah, not for things. Very happy with that. That's it.
Okay, so I don't know if there are questions online. If not, we can thank Laura again. Thank you. We'll be around what's in there.